we have started recording. So welcome for this session. So this session we start with the seminar by Enrico Barausse from CISA Trieste, and the title is GW Generation Beyond GR. Enrico, the stage is
Thank you. Thank you. First of all, yeah, thank you, Sudipto, and all the organizers for inviting me, even though just remotely. I wish I could visit in person, of course, just like everybody else. So today I will focus on the generation of gravitational waves beyond GRs. We heard a lot about parameterized tests and also about propagation of gravitational waves in the previous talks. Today I will try to take a more top-down approach. So I will try to show you how gravitational wave generation can be predicted in theories that go beyond GR, and how that can be connected whenever possible to parameterized tests. So this is the plan of the talk. So first of all, I will try to motivate why I want to go beyond GR and how I want to go beyond GR. And these are two important questions to understand the following. So after this introduction, I will focus on how deviations from GR cause deviations from the strong equivalence principle in systems involving compact objects. And I will focus, of course, on black holes and neutron stars. And this will allow me to draw implications of deviations from GR on the generation of gravitational waves during binary inspirals. So this will make me, this will allow me to make a connection to parameterized tests of the inspirals that we heard about in previous talks. We'll then move forward in frequency, and at higher frequencies, of course, you have the merger. The merger is, of course, much more difficult to model beyond GR. So we heard a few questions about the Cauchy problem and numerical relativity and how that can be applied beyond GR. I by no means have a complete answer to that, but I will try to present attempts that have been made by various people, including myself, about trying to model GR effects during the merger. And then naturally we'll move on to ring down tests of the Norher theorem. And I will also talk about what I like to call post-ring down effects or near horizon effects. So Vitor talked already about about this yesterday. I will take a slightly different angle on them, but I will talk about superradiance firewalls or model, phonological model for firewalls. And I will try to make a connection to violations of Lorentz symmetry in gravity, and in particular to the concept of universal horizon. But without further ado, let me go to my first real slide. So why do we want to go beyond GR? Of course, there's a motivation for going beyond GR is that we know GR is a classical theory, so which is not power countingly normalizable. We see it simply by dimensional analysis. So we would want to have a quantum gravity theory. So this is not my my main motivation, mainly because if you believe in quantum gravity, the gravitational waves are quite useless to put constraints on that theory because their energy is much lower than the Planck scale or any other scale that's relevant in particle physics, essentially. So another take, however, is to look at cosmology. So in fact, we all know that there is evidence for a dark sector, for dark matter and dark energy. So we heard yesterday from Vitor about that. One interesting thing is that cosmology, when it comes to the gravitational properties of the systems that we study, is not very different from the solar system. So what I try to plot here in this figure are a host of cosmological systems. For instance, I put the Milky Way and the CMB, and at the same time I put planets and the sun. And in the x-axis, I plot the velocity of the system, characteristic velocity of the system over the speed of light. In the y-axis, I plot the strength of the gravitational field. I computed simply the Newtonian potential and divided it by c squared so as to make it a dimensionless quantity. And I also put in the top right corner systems that generate gravitational waves, so system of 2 neutron stars and systems of 2 black holes. And there are two things that, and in the color code, I put the characteristic acceleration of the system, which, if you want, is a proxy for the scale of the system. So bluer colors correspond to larger systems, cosmological systems, whereas more greenish or more red colors correspond instead to smaller scales. There are two things that you can notice. The first, well, I guess you can notice that first of all, gravitational wave emitting systems probe the strong field and highly relativistic regime. So they involve speeds which are comparable to the speed of light and very strong gravitational fields. So there is no, so it's interesting, it's inherently interesting to look at these systems to test gravity, because it's a regime in which gravity hasn't been tested at all so far, and which could therefore yield more information about possible deviations from GR. The other important thing is that both the solar system and cosmology occupy the same region in this plot, save for the color code. So they both involve weak fields, weak gravitational fields, and non-relativistic or mildly relativistic velocities. So from the point of view of gravitation, these two systems are completely equivalent except for the scale, which in GR doesn't matter because GR is scale invariant. So a black hole of 1 solar mass behaves just like a black hole of 10 to the 9 solar masses. So the predictions of GR scale with length. There is no intrinsic length in GR unless you put a cosmological constant. So if you want to modify GR to try to explain away dark energy, or what we call a screening mechanism. So you need a way to screen deviations from GR in local scales so as to pass solar system tests, which are in perfect agreement with GR, and free instead deviations from GR on cosmological scales. This is what we mean by screening mechanism. And there are various implementations of the screening mechanism in theories beyond GR. And I will try to make the case that they actually may have they may produce very large deviations from GR in the gravitational waveforms in the merger, because they are very nonlinear effects. So this is a little bit my motivation for going beyond GR. First of all, because we want to test or secondly, because it helps, it offers the possibility to shed light on the screening mechanism and therefore on alternative explanations for dark energy and dark matter. So I spent a lot of time on this slide. Let me go to the next. How do I want to go beyond GR? Well, a roadmap for this is provided by Lovelock's theorem, which tells you essentially that the GR is the consequence of 5 hypotheses. First of all, that gravity is described only by essentially tensor fields, so a metric. Secondly, that the field equations should depend only on second order derivatives, no higher derivatives, that we should be in 4 dimensions, 3+1 dimensions, that we have diffeomorphism invariance, and that matter couples minimally to gravity, so that there is no violation of the weak equivalence principle. These are the 5 ingredients to GR that are formally implemented in Lovelock's theorem. So whenever, in all the modifications of GR that I know, or at least all classical modifications of GR, you break one of these assumptions. And here in this chart, I put various examples. This is by no means an exhaustive list. But what I want to stress is that all these 5 ingredients, actually any one of these assumptions involve adding extra fields in our description of gravity, adding extra gravitons. For instance, if you want to break diffeomorphism invariance in massive gravity or in what we call Lorentz varying gravity, you do so by introducing other dynamical or non-dynamical fields. For instance, in Lorentz varying gravity, you add an extra vector or scalar field that violates Lorentz symmetry. If you of course, if you include higher derivatives, typically that corresponds by using a reduction of order methods that corresponds to adding new fields. If you add higher dimensions, you can recast the the components, for instance, of the metric tensor in the higher dimensions with extra fields. So each of these, essentially all the gravity theories that I know of that extend GR involve adding extra gravitational fields.
Can I ask a question on the previous slide?
Sure, of course.
Can you go back to that slide?
I don't know how to go back. Yeah, I'm trying to. Yeah, here it is.
Okay, so where does Einstein, Cartan, Sciama-Kibble theory of gravity lie?
That's a good question.
Because I don't.
Einstein, Cartan, there is no. On the other hand, in vacuum, but you have torsion, right? Yeah. So torsion is dynamical.
Yeah.
So in Einstein, Cartan, torsion is dynamical, so it's an extra field. I got it. Yeah. I'm not an expert about that, but I think torsion, yeah, in vacuum, in fact, it reduces to GR, so torsion is
only in for fermionic matter, it sort of deviates.
Yeah, fermionic matter, torsion becomes
at very high gravities.
Yeah, so it becomes an extra field, so it belongs to this. Can you see
and is Lovelock's theorem valid for Einstein-Cartan gravity?
This is a general theorem.
Okay,
this is a general theorem, so it applies to any gravitational. Well, the statement is the following: that if you want to have Einstein's equations, you have these 5 ingredients. So it doesn't apply to a specific theory; it applies to all theories.
Thank you.
Okay, no problem.
Sorry, can I interrupt you again? Sorry.
Of course, yeah.
Yeah, the first slide. I was wondering, is there any observational evidence at all where you see that there's a problem with GR?
No, not that I know of. We heard about parameterized talk. Well, the observation, if you believe the dark sector doesn't exist, cosmology is is one of these pieces of evidence. But of course, you can explain all of cosmology with just a cosmological constant. This, of course, raises the question of what produces the cosmological constant. And we know that the scale of the cosmological constant is very low with respect to the scales that you would predict from active energy. So it's not that the cosmological constant is flawless, but I agree, everything could be explained just by a cosmological constant.
Well, Big Bang singularity, I mean, that's the clear evidence that GR breaks down, right? And also arrow of time.
No, but
yeah, but those are higher energy. Yeah.
See, the breakdown of GR in the ultraviolet would simply mean that you have to replace the classical theory by maybe a quantum gravity theory. So that's a separate question altogether. Right?
Yeah, no, I totally agree.
Are concerned.
Yeah, I totally agree. There is no infrared evidence for deviations away from GR. But I don't think this makes it less interesting, because I will try to explain the following, because actually we can weed out many of these alternatives using gravitational wave observations. So, okay, so let me go to my next slide, unless there are other questions about this. If not, I will, yeah, so I mentioned that essentially in all gravitation theories, classical gravitation theories, low energy gravitation theories that I know of, an extra polarization for the graviton is added. The simplest example is Brans-Dicke theory, where you add a scalar field. And this begs the question, of course, of how you couple these extra graviton polarizations to matter. And of course, the simplest thing to do is to couple these new gravitons minimally to matter. Said otherwise, you can think of coupling the matter fields, which I indicated here by psi, I hope you see my cursor, only to the metric and not to the extra fields. And why do you do this? Because you don't want to introduce any fifth forces, at least at 3 level, lowest order in perturbation theory. So if you were to couple matter to a putative scalar graviton polarization, of course, you would introduce scalar forces, and there is no evidence for such forces in particle physics experiments. However, this is something, of course, you can do, but this, of course, doesn't prevent these extra graviton polarizations from coupling to matter when you go to next orders in perturbation theory. So, in other words, think again about Brans-Dicke theory, to which I will come back in the following slide. In Brans-Dicke theory, the scalar field couples non-minimally to the metric, and the metric then couples to matter through this non-minimal coupling. So essentially, so when you go to next order in perturbation theory, the metric perturbations mediate an effective interaction between matter and the scalar field. So even though fifth forces do not appear at tree level, they appear at next order in perturbation theory. If the metric perturbations are large, because this effect is mediated by the metric perturbations, so if you want this effect to be important, metric perturbations need to be large. So I will explain this in more detail in the next 2 or 3 slides, but this has been known for a long time, since the 60s and 70s. It's known as Norbert effect, so it's used every day by people such as Norbert Wex, who do binary pulses. I think Norbert is in the audience, I saw him before. The equivalence principle, therefore, so this means essentially that the equivalence principle is violated for strongly gravitating bodies. So if the metric perturbations are large, as they are in neutron stars and black holes, this effective interaction between the matter fields and the extra gravitational polarization will be present and will cause deviations from the universality of free fall. So, another way of saying the same thing is, which is perhaps more physically understandable, is again to think about the Stroman theory par excellence, the Brandstike theory. So this was the simplest modification of gravity, and that was introduced in the early days of in the golden days of general relativity in the 60s and 70s, and it involves introducing an extra scalar field. So this scalar field couples no minimally to a metric because it renormalizes the Planck mass. By the way, can you see my cursor?
Yes, we can.
Okay, so you see here that phi renormalizes the Planck mass essentially, or renormalizes, if you want, big G, the gravitational constant. And then there is, of course, this kinetic term for the scalar field. Now, the fact that phi renormalizes big G should raise a red flag, because we know that in relativistic theory, all sources of energy gravitate, and in particular also the binding energy gravitates. So if you have a neutron star whose mass is comprised by 10% of its mass is comprised, is given by the binding energy. If you change big G, you change also the binding energy of the neutron star, and therefore the mass of the star. So the mass, and because phi can be a function of position, because phi is a field, that means that the mass of the star can become a function of position. So as the star moves, the mass of the star can also move. And of course, this can have a big effect on motion. The same, by the way, happens in what we call Lorentz violating gravity, to which hopefully I will be able to come back in the end if I have time. These are cases in which you introduce a preferred frame for gravitational physics. So there is an absolute time, just like in the old Newtonian mechanics, just like in Newton's interpretation of Newtonian mechanics. So there is a preferred frame, a preferred time foliation of your space-time. And when a star moves with respect to this preferred frame, its physical properties are different than if it was at rest. So the gravitational mass of a neutron star in these theories depends on the velocity of the body itself, which is something, of course, that does not depend, that does not happen in GR, in which the mass is always constant. It doesn't depend neither on position nor on velocity. So this, of course, as I was saying, has effects on the motion, because you remember the derivation of geodesic motion in GR is a consequence of a variational principle. So you can write a variational principle for a binary system as a superposition of two actions like this. So you write the action for a single classical particle in GR, and that's simply the integral of the mass times the line element. And in GR, because the mass is constant, the mass drops out of this integral. You can take a variation of this action, and you get the geodesic equation. So here, the masses will not be constant anymore. They will depend, in the Brandstike case, on the scalar field, in Lorentz violating gravity on this field that breaks Lorentz symmetry. So you'll have something else on the right-hand side other than zero. So you not have the usual geodesic equation, but you have something else. And what will be, which will resemble the geodesic equation, but will have a source on the right-hand side. And this source will involve derivatives of the metric, of the mass with respect to the extra fields present in the action. And this is what we call sensitivities or charges or hairs. They go by different names, but they are essentially sources in the geodesic equation, which cause deviations of the strong equivalence principle. Just to give you, again, a more intuitive idea of what is going on, this is a very simple thought experiment that I did in a paper by D in 1969. The plot is mine, so I apologize for the poor plot, the poor sketch. But essentially, it goes as follows. Suppose you have a gravitational theory in which the binding energy is function of position. So a gravitational theory such as Brand-Stickle, in which the big G, the Planck mass, is renormalized by some extra field, just like Brand-Stickle. So in that case, the binding energy becomes a function of position because the binding energy depends on big G. And you can think of this thought experiment. Suppose you have a collection of n particles of mass n at the ground floor of a building, and you have these test particles collapse into a star. So this will release, of course, gravitational energy as heat. So the star will heat and will shine. So you will release some energy. Then suppose you raise this star to the second floor of your building. To do that, you'll have to perform some work against gravity. And let's suppose the gravitational acceleration here felt by this body is called A. And then you can calculate what this work is. And I suppose that here at the second floor or first floor, if you're in the US, I guess, a nuclear reaction makes the star burst, or suppose the star goes supernova, so it explodes. So you have to provide energy to break the star up back into particles, and then you drop these particles one by one to the ground floor. And and let's call G the acceleration felt by these individual particles. And then you apply simply energy balance. So if you do that, you find that G and A, G, the acceleration felt by the single particles, and A, the acceleration felt by the compact object, are not the same, and they differ by the gradient of the binding energy with respect to the height. H here is the height. So of course, in GR, the binding energy is constant, so it doesn't depend on whether your star is at the first floor or second floor. So here in GR, G and A are the same. So test particles move exactly on with the same acceleration. But theory, such as Brand-Stickle, in which the binding energy is not constant, the two differ. And this is exactly what I was trying to refer to before as violations of the strong equivalence principle. So compact stars in modified gravitational theories move differently than test particles. So why am I spending all this time on this point? Well, because these violations of the strong equivalence principle have very important implications for gravitational wave emission. And you can easily understand that, because if the motion of stars is changed away from geodesic motion, this will have implication for neutron star binaries, binary pulsars, black hole binaries, and so on and so forth. So gravitational wave emission will be impacted. And in particular, what happens is that you typically or generically produce monopolar or dipolar gravitational wave radiation. Of course, monopolar and dipolar radiation, we never heard of them in GR for good reasons, because they don't exist in GR. The reason why they don't exist is into the reason why in electromagnetism we have no monopolar radiation. So in Maxwell's equations, you have electric charge conservation built in. So the Maxwell equations imply conservation of electric charge, and this prevents monopolar radiation from being produced. So in GR, similar happens. You can try, for instance, to write down a dipolar gravitational wave in GR, simply based on dimensional analysis. For instance, you can try to write down the mass dipole simply up to factors, this would be the integral of rho, the density of the system, times the position integrated over the volume. So this would be the mass dipole, the equivalent of the charge dipole in electromagnetism. And then based on dimensional analysis, you could try to write down a gravitational wave. So we know that the gravitational wave strain is dimensionless. And simply based on this observation, if you just have M1, G, and C3 and C, the only dimension, the simplest dimensionless combination that you can write is G over C cubed times M1 dot. And if you compute what M1 dot is, it turns out to be given by the linear momentum of the system, which in GR is conserved. So if you try to write down a dipole gravitational wave amplitude or gravitational wave strain in GR, it's not a wave at all. It's a static Newtonian-like potential because the linear momentum of the system is conserved. So this is not a wave. It doesn't carry any energy in GR. So in GR, you can do the same. You can perform the same calculation for monopoles, for monopole radiation in GR. Monopole radiation in GR is forbidden by conservation of energy, and dipole radiation in GR is forbidden by conservation of momentum. This argument, in fact, is a cartoon-like argument, but can be more rigorous, can be made more rigorous in post-Newtonian theory. So now, suppose you have a GR extension in which, as I was saying before, the effective mass of a compact object depends on the, for instance, on the scalar field in the case of Brandstickhen. So this was the case of Brandstickhen. And now let's try to compute what the derivative of the dipole mass moment is in Brandstickhen. So at least at cartoon level. So you plug back your Dirac delta model for the density in the expression for M1. So here you'll have M1 times X1 plus M2 times X2, but M1 and M2 would be functions of phi. So here on the right-hand side, instead of having 0 as you would have in GR, you will have, again, a source term that depends on these sensitivities or scalar hairs, which, I apologize, which were defined, sorry for going back and forth, which are exactly the derivatives of the mass with respect to the scalar field. So these are, again, coefficients, which are called sensitivities or sometimes scalar charges or hairs, which you can compute in a given theory and which parameterize deviations from the strong equivalence principle, or if you want, from the universality of free fall. And they produce in particular also dipole gravitational wave emission, which is importantly a -1 PN effect. So it appears at frequency, at lower post-Newtonian orders, the quadrupole gravitational wave emission. So it's much more important than quadrupole emission during the in-spiral of a binary system. Of course, the key thing here is that this S1 and S2 depend on the nature of the bodies under consideration, exactly because we break the equivalence principle. So the equivalence principle states that objects of different nature follow the same geodesic trajectories. When you go away from GR, objects of different nature need not follow the same trajectory. So you need to compute these coefficients, S1 and S2, for a given theory for each for different kinds of bodies. So neutron star sensitivities will be different than black hole sensitivities, for instance, and neutron stars of different compactnesses might have different sensitivities in general. So the difficult thing is actually to compute these sensitivities in a given theory, essentially because you need to solve for stellar or black hole structure in these theories, and then consider how a given star or a given black hole responds to a change in the boundary conditions for instance, for the scalar field in the case of Brandstickhen. So these sensitivities tell you how much the mass changes when you change the boundary condition, the background value of the scalar field in which the star is immersed. So think of a star moving in a scalar field. So we want to see how much the mass of the star changes when you change the background value of the scalar field in which the star lives in. So technically, this is translated into finding, for instance, in the case of stars, Tolman, Oppenheimer, Volkov solutions with different boundary conditions, and then comparing these solutions. So it's it's not rocket science. I mean, it's not difficult, but it takes some effort to do it for many theories. So a few years ago, with collaborators, I've started this program of computing sensitivities for stars in theories with Lorentz violations in the gravitational sector. And you have to do it for different equations of state. The results will depend on the compactness. So it's quite an involved calculation. So recently we did it also for black holes. But the payoff is quite remarkable. And the reason is that these sensitivities, again, parameterize dipole emissions of gravitational waves. And so far, we have no evidence at all of dipolar emission of gravitational waves. The most famous example is binary pulsars. I think most of you guys are familiar with this. These are systems of two binary neutron stars. The damping of the period of these binaries involving at least one neutron star, one spinning neutron star, one pulsar, are in perfect agreement with the predictions of GR. So we have no evidence of dipole emission whatsoever in binary pulsars. And this allows us to put very tight constraints, for instance, on Lorentz violations in gravity. So this is an example of what we call Hojava gravity or chronometric theory. So it's the infrared limit of a Lorentz violating quantum theory of gravity, in which deviations from Lorentz symmetry can be introduced already at low energies and are parameterized by two parameters, lambda and beta, in this plot. So GR is the origin of this plot, and the allowed region, when you include just basic requirements such as stability, essentially absence of ghosts and gradient instabilities, and agreement with solar system tests, is given by the blue region here. And remarkably, well, cosmology already puts constraints on this parameter space. So if you include cosmological bounds, this parameter space is reduced. But more importantly, if you include pulsars, in particular the requirement that there is no dipolar radiation in binary pulsars in these theories, you essentially reduce the available parameter space for the theory to a tiny triangle close to GR. So I'm here in this inset, I'm plotting on the region near the origin. And all you're left in your theory is this purple triangle when you impose that no dipole radiation is produced in binary pulsars. Remarkably, this is the same. Recently, there was yet another bound on these theories coming from the fact that the speed of gravitational waves must match the speed of light to within a part in 10 to the 15. I'm sorry, in 10 to the 15. And this turns out to be essentially a very similar bound as the one you get from dipole radiation. So it's the red line here. So this is in a sense to, yeah.
May I ask you a small question?
Yeah.
So it seems almost all the parameter space is ruled out if I include all.
Actually, no, it's actually tricky. So there is one direction that seems, yeah. So from lambda from 0 to 0.1 is still allowed. The question is this really a different theory than GR, or is it just GR in disguise?
Okay.
This is something I'm not sure about. I could give a full talk on whether this is the same as GR or not, but the answer is I don't know. All observables when one computes seem to be the same as in GR, but if you do a canonical analysis of the canonical constraint analysis, it's not GR. So yeah.
So also,
yeah. So to answer your question.
Okay.
Sorry. Go ahead. Go ahead.
So this is also Lorentz violation only in the gravitational side, right?
Yes. Yes.
So matter to be QA.
Yeah, this of course, in these theories, we're imposing that there is no percolation of Lorentz violations to matter, so that we assume that there is a mechanism to restore Lorentz symmetry in matter at low energy via perhaps renormalization group flows, and that is not guaranteed, because the renormalization group flow is only logarithmically convergent to GR at low energies. But yeah, we're assuming that there is no violations of Lorentz symmetry in matter.
Okay, thanks.
Sorry, a follow-up question of Sudipto's question is that, you see, when you say Lorentz violation, see, Lorentz invariance is actually local Lorentz invariance, which is a gauge invariance, right?
Mm-hmm.
In GR. And when you say you violate it, you're violating a gauge symmetry, which has very severe consequences in ordinary gauge theories. It will lead to all sorts of problems. And if you have any plans of quantizing the theory, you're going to end up with a
actually, but actually the reason why we break, or more other people also break the symmetry, is that it actually makes the UV properties of the theory more appealing. In fact, not only makes the theory power counting renormalizable in the UV, it also makes the theory perturbatively renormalizable. It was actually shown very recently that not only at power counting level, but also at perturbative level, the theory is renormalizable in the UV. The real question is how, as far as gravity is concerned, there are no, I think it makes the theory more appealing, but as Sudipta was asking, the real problem is how you protect the matter sector, in which we see no evidence of Lorentz violations from the violations you introduce in the gravitational sector, because of course the gravitational sector is coupled to matter. And there are a few ideas about that, in particular, as I was saying, renormalization group flows. But,
sorry, Enrico. The problem is that since the coupling is gauge invariant, if you break gauge invariance in any one sector, you cannot protect the gauge non-invariance from percolating into the other sectors.
Yeah, but the question is how, it depends how large Lorentz violations you accept in the matter sector, whether they're small or large. And if the renormalization group flows to GR very fast at low energy, flows to Lorentz invariance very fast at low energies, then you might not have a problem. In fact, it was shown that it flows, but only at logarithmic rate, which is not satisfactory yet. So I agree that there is potentially a problem. I don't think it's just because you violate Lorentz symmetry, it automatically means that that we have a problem.
I'm just saying what my experience in quantum field theory in flat space time is. If I violate a gauge invariance, I have anomalies, and anomalies are a severe problem with regard to unitarity of the theory.
Okay, I'm happy to discuss. I'm happy to discuss offline about this. But the Lorentz symmetry, I know that this slide raises lots of questions, but I just wanted to be an example. I'm happy to talk about it later about unitarity. But again, I think at least in vacuum, there is no violation of unitarity whatsoever, and the theory becomes renormalizable. But let me postpone. I'm happy to discuss offline about this. What I wanted to, the next slide is about a different theory, so we don't, hopefully this is going to be less controversial. The absence of dipole emission binary pulsars can be used not only in Lorentz violating gravity, which was supposed to be just an example. It was historically used, for instance, to constrain scalar tensor theories of the Wagoner-Bergman type, or theories that resemble Fierz-Jordan and Brand-Stike. So this is, I don't know if Norbert is still there, but this is something that Norbert invested a lot of time in. So these are theories where you have, again, an extra graviton field, which is sourced by the Ricci scalar of the background. And this causes, in particular, if you take a field theory approach, there should be linear terms in R on the right-hand side, but there should also be terms that depend, there should be terms that are independent of the scalar field, but there should be also terms like this that involve phi times R. And these, in fact, cause very large scalar charges or sensitivities for compact neutron star systems. And this is called spontaneous scalarization. I'm sorry for going back and forth, but I have it in the next slide. So it's essentially a phase transition inside a neutron star. So if you have a term that couples Ricci and phi on the right-hand side of the field equation for the scalar field, this induces a tachyonic instability on the GR solution. And it makes the star evolve to a configuration where the scalar field is highly non-trivial and the scalar charge or sensitivity is very large. In fact, it's you can, as the Moore showed long ago in the 90s, it's a critical phenomenon. It's a phase transition triggered by the compactness of the star. So if you have a very low compactness star, such as the Sun, you have no deviation from GR whatsoever. At large compactnesses, for instance, for neutron stars, deviations from GR start kicking in. Let's see if I can go back. Yeah. And this actually allows, this would produce very large dipole fluxes, and this allows to put severe constraints on this beta term in neutron star systems. For instance, these are, this is a figure, I don't know if it is published, but essentially the allowed parameter space for these parameters alpha and beta is the one below these curves, and these curves correspond to different pulsars. And as you can see, negative values of beta, which are those giving this tachyonic instability or spontaneous scalarization, as we call it, are ruled out. So this is an example of a nonlinear effect that can take place inside compact objects, which causes large deviations away from GR and which can be excluded already from current data. So this is why I find it interesting.
Can I ask a dumb question on this?
Yeah, there is no dumb question, but please go ahead.
So yeah, but I still feel embarrassed to ask. So I guess this spontaneous scalarization occurs no matter whether you treat this in Einstein frame or Jordan frame?
No, it's actually independent. I mean, of course, if you plot the metric in the Einstein frame or the Jordan frame, they will be different. But when you compute observables, there is.
But sometimes there are like differences, especially in.
Well, at least at the classical level. It depends how you couple the matter. Of course, if you have a theory in which you couple the matter to the Einstein frame metric, and another one in which you couple the matter to the Jordan frame metric, the results would be different. But as long as you're consistent and as long as you're classical, there is no difference between the two.
Okay, thank you.
At least at classical level. I'm not sure. At quantum level, there might be different, but we don't believe these are quantum. I mean, we treat them as classical theories usually. So I've been talking a lot about binary neutron stars and binary pulsars. How about dipole? Is there a dipole emission in black hole binaries? Up until a few years ago, people believed that no, there wouldn't be any dipole emission in black hole binaries. And the reason was exactly the intuition from Fierz-Jordan Brans-Dicke-like theories, in which the scalar field is sourced by the Ricci scalar. So of course, for a GR black hole, the Ricci scalar is 0. So the source of the right-hand side of this equation would be 0, and the scalar field wouldn't be sourced. There are, of course, loopholes. So you can think of cosmological boundary conditions. There are a few loopholes to this, but in general, I remember I bet with Cliff Will, who was betting about this with colleagues. The common law was that there wouldn't be any dipole radiation, at least in Fierz-Jordan Brans-Dicke-like theories. And I think this is a fair assessment. So in general, there is no dipole radiation for black hole binaries in this kind of theories. But of course, if we treat these theories as effective field theories, there is no reason why we should focus only on a coupling between Ricci and the scalar field, which is the one we find in Brans-Dicke-like theories. We should include all possible couplings. For instance, at the next order in curvature, there could be couplings between phi and R squared, or phi and the Kretschmann invariant, phi and the Potryagan density, phi and the Gauss-Bonnet invariant. And in general, these will not be 0. They will produce sources to the scalar field equation which are not 0 on black hole background. So there is no reason why black hole's charges or scalar charges shouldn't be non-vanishing in more generic gravitational theories. Of course, not all those terms have the same standing. Some of them are problematic. So typically they will introduce couplings of this kind. They will introduce Ostrogradski ghosts in most cases. So for instance, this coupling between both this brownish and purplish terms and also the green term will produce Ostrogradski ghosts in general. This might not be a problem if you treat the theory as an effective field theory, but well, if we want to do calculations, for instance, in numerical relativity, this is a problem. So these terms will produce in general ghosts. There is, however, one term that doesn't produce ghosts, which is a coupling between the Gauss-Bonnet invariant and the scalar field. This goes under the name of dilatonic Gauss-Bonnet theory, at least in the gravitational wave literature. And in fact, it produces no ghosts, and it produces at least no Ostrogradski ghosts. It has second-order field equations. It belongs to the Hordensky family of scalar tensor theories, and remarkably, it gives no sensitivities, no scalar charge for neutron stars, but non-zero charges for black holes. So we're in the opposite situation as for Brandstike theory. In Brandstike theory, you have scalar charges for stars but black holes, whereas you have here we would have scalar charges for black holes, but not for neutron stars. So one question then you can then ask is, well, but what are these black hole charges? Are they generally small, or could they be large, just like in spontaneous scalarization of neutron stars? So can you have something like spontaneous black hole scalarization? Well, this is in the last, in fact, 2 years at most, it was realized that specific couplings between the higher order curvature invariants and the scalar field could produce scalar charges even for black holes, could produce spontaneous scalarization, could produce non-perturbative scalar charges also for black holes. So we could have something like the Damour espoused as spontaneous neutron star scalarization, but for black holes. And it's actually quite simple to understand that. So think that these functions, f2, f3, or f4, are quadratic in phi, in the scalar field. Then k, or the Pontryagin density, or the Gauss-Bonnet invariant, would not be zero on a black hole background. For instance, we know that the Kretschmann invariant goes as 1 over r to the 6 for a Schwarzschild black hole, and the same for G. So these invariants are not zero for black holes. So they produce essentially an effective mass term. So if you think of K as non-zero and F2 as quadratic, you can produce an effective mass term on black hole backgrounds. And according to the sign of the coupling, according to the sign of F2, this effective mass term could be well behaved, or it could correspond to an imaginary mass. So it could give a tachyonic instability on a black hole background. So this was realized by Silva and collaborators in 2018 for the Gauss-Bonnet invariant. And then there was a long list of papers, and this is not an exhaustive list, which show that this is quite generic. Whenever you have a quadratic coupling between phi and curvature invariants, this essentially always happens as long as the sign of the coupling is quote unquote the wrong one, the one giving tachyonic instability. And this can actually produce very large scalar charge for black holes. So more recently, we realized, in fact, that since some of these curvature invariants change sign when you go to the rotating case, so for instance, Gauss-Bonnet can be positive, is in general positive for Schwarzschild and becomes negative for extremal Kerr, whatever the sign of the coupling that you choose, you will always have, even if you don't have spontaneous black hole scalarizations or tachyonic instabilities in the non-rotating limit, you'll always have those tachyonic instabilities and therefore spontaneous scalarization at high spins. So this is some work we did a few months ago. So we realized that for quadratic couplings between the Gauss-Bonnet invariant and the scalar field, even though you choose the sign of the coupling so that you have no no, if you want, deviation from Schwarzschild, or no large deviation from Schwarzschild, at high spins, you'll always have a tachyonic instability. So here we show the details are perhaps not important. This is the time scale of the tachyonic instability. So you have a tachyonic instability occurring on dynamical time scales, which triggers the formation of a large black hole scalar charge. So why, yeah.
Yeah, just one question. So the black hole that you are considering, is it a solution of the full action, or is it just a solution of GR, or in some approximate sense?
Okay, so in this paper here, since it's the first work, we're just considering evolutions of the scalar field on a fixed black hole background, and show that the scalar field becomes tachyonically unstable. In other papers, in the previous papers by Silva, Doneva, etc., they did both. They considered both the evolution of the scalar field as a test field, and show that it's tachyonically unstable, and then show that and then computed the full scalarized black hole solution. We didn't do that. I don't know if this answers your question, if this is what you meant.
Yeah, thanks.
Yeah, so it's still preliminary, or if you want, it's a first step. Mainly, we didn't do it because, of course, to find axisymmetric solutions is much more difficult than finding spherical solutions. So technically, it's more challenging. But we plan to do it unless, I know that Carlos Herrero is working on this, so maybe he'll get there before.
So this Gauss-Bonnet invariant is for the Kerr black hole, if I'm correct.
For the Kerr black hole, yes, for the Kerr black hole. That's why it produces an effective mass, which can change character, because Gauss-Bonnet changes sign in Kerr when you go from small spins to high spins. The mass can go from real at low spins to imaginary at high spins, and this is what triggers the tachyonic instability.
Okay, thank you.
No problem. Okay, so I need to speed up a bit because this is taking. I was relaxing because I thought I had lots of time. Well, why is this important? Well, because now we see black holes binaries with LIGO Virgo, hopefully tomorrow Kagra and LIGO Indium, and so this was shown already, I think, by Arun yesterday. So we can't put very large constraints on dipole emission with current detectors, although things are improving. But with LISA, if we consider LIGO Virgo binaries as seen in LISA, we could actually constrain the difference between the sensitivities or scalar charges of the two objects to within 10 to the minus 8, which is essentially the same accuracy with which we can exclude dipole radiation in binary pulsars with current data. So LISA combined with ground-based detectors will be an exquisite precision tool for testing these effects. Okay, so I'll skip this slide. So more recently, we looked at this in a full Bayesian framework because we were worried about the response, the LISA response, which is not trivial for LIGO Virgo binaries because they stay in band for a long time. But essentially, our Bayesian analysis that take into account the full response confirm the results of our initial estimate. Okay, so I'll go very quickly through this. Yeah, I'll go very quickly also through this slide. This is just one note of caution. When we talk about testing dipole emission with gravitational waves, it's a -1 PN effect. There are other effects, more mundane than deviations of GR, that can mimic dipole radiation, or low, if you want, negative PN order terms. I think this was mentioned by previous speakers. I think certainly Vito yesterday mentioned that dark matter can produce negative PN order effects in the phase. Actually, even more conservatively, accretion of baryonic matter of gas onto black holes can produce a -4 PN term, which would be detectable by LISA. So in this recent paper, we considered how accretion would be detectable by LISA if the LIGO Virgo black holes are in the LISA band and they accrete, and we find that we can measure them if the adding for some people this could be SG could foreground, because this could mask actually whatever deviation from GR would be in the data. And this is quite interesting because recently there was a claim that some of the LIGO black hole binaries might have a counterpart exactly due to the presence of gas around them. So this is something to keep in mind. So I'll skip this slide. So I promised that I would talk about mergers, which is my favorite topic. So I think I will devote some time to this. So this question popped up a few times. So do we have, can we make actually predictions for the merger in specific gravitational theories that deviate from GR? Of course, this requires that the Cauchy problem, that is the initial value problem, is stable, quote unquote. What I mean by stable is in technical terms that it is well posed, so that it depends in the Hadamard sense continuously on the initial data. This is a mathematical requirement, which, however, is necessary to perform numerical simulations, because, of course, if you have a Cauchy problem which is not continuously dependent on the initial data, numerical relativity simulations can be stable. The results will depend on, they will not be stable. So technically, a sufficient condition for having a well-posed Cauchy problem is symmetric strong hyperbolicity, which means essentially that your equations need to be wave equations. So in numerical relativity, we like wave equations, or at least for the Cauchy problem, we like having wave equations. If you have an elliptic equation, you can't solve it as an initial value problem. It's a boundary value problem. So the question is, is the Cauchy problem well posed for the theories I've been talking about? Well, it certainly is for Brans-Dicke type theories. But in fact, simply because the dynamics of these theories in vacuum reduces to that of GR. So for Brans-Dicke theories, this is not a problem. We can perform simulations, although they will be trivial in vacuum at least. For Lorentz varying, I'm quoting here Lorentz varying gravity. I hope I will not open a whole new can of worms, but simply because I recently showed in this paper that this theory actually does allow for a well-posed initial value formulation, even though it's so complicated that no numerical relativists so far picked up on it, because it involved a tetrad. It's a tetrad-based formulation of the theory that we could show it's symmetric hyperbolic. And then I think the judge is still out for many other theories, for most theories that people are interested in, theories of cosmological interest, so Dost, cubic Galileons, K-essence, Einstein-Dillon Gauss-Bonnet itself, even though it has no Ostrogorsky ghosts, is known not to be globally well posed. This was a recent work by Ripley and Pretorius. There is other work, important work by Bernard, Lune, and Lehner, Figueres, and Frank in this year. Of course, I have mixed feelings about this. When I talk to people from the effective field theory community, they're not really impressed by the lack of a well-posed Cauchy value problem, because they say, well, we could always interpret the theory as an EFT. There are ways in which you could incorporate this thinking into numerical simulations, but they're not. By definition, an effective field theory works only at scales below the cutoff, and essentially, yeah, the deviations that you can get from GR will always be small. So it's not clear how these attempts to perform numerical simulations in gravitational theories that are interpreted as EFTs captures the nonlinear dynamics that is crucial to many of these theories, for black hole scalarizations, for the screening mechanism that I mentioned at the beginning. So there are attempts in this sense by Okunkova, Stein, collaborators at Caltech, Cornell, by Lehner at BI, but it's not clear how much we capture the nonlinear dynamics. So we might miss on the most important effects. So an example of a nonlinear effect that you can capture if you have a well-posed initial value formulation is the following. So it's a very old paper, 2013, that I wrote in collaboration with Carlos Palenzuela, Marcelo Pons, and Luis Lehner, in which we show that for Brand-Stickett type, or if you want, the more positive Fourier type theories, so the same theories that produce spontaneous scalarization in stars, you can also have very strong nonlinear effects, if you want, phase transitions in the merger phase. So what we do is to, essentially what you see is that you start, for instance, with a star that has a scalar charge, the red point here. These are snapshots of the time evolution. And the star that has no scalar charge. So the color code here is the strength of the scalar field. So the scalar field is larger when the color is redder. So you see that one star has a scalar field, non-trivial scalar field, and the other star has very little scalar field. But when the two stars, they get closer than a certain critical threshold, then also the second star develops a scalar charge. And this actually triggers a much earlier merger than you would have in general relativity because of the interaction of the scalar charges of the two objects. So yeah, I'm sorry, the plots must be very small when seen on your screen. Here I have the separation of two neutron stars as function of time for GR in black, and for different scalar tensor theories of the Damour positive Fourier type. And you see that when the parameter beta is even mildly small, minus 4.2, which is still allowed by binary pulsar data, you trigger an earlier merger with respect to GR, and this causes the formation of a rotating bar. So this is the gravitational wave signal, or actually the derivative of the gravitational wave signal, psi4, second derivative. And you see that the blue and red curves, which correspond to non-GR, they have these high frequency oscillations, which are due to the formation of a rotating bar. And this happens also if neither star has a scalar charge in the beginning. So this is why we call it dynamical scalarization. And you can interpret it as in the same as a phase transition again. So for spontaneous scalarization, the phase transition was triggered by the compactness of an isolated star. So here, what matters is the compactness of the binary. So when the binary is far away, so when you have a small effective compactness for the binary, so total mass over separation, you have the minimum for the scalar field is 0, so you essentially have GR. But when you're above a certain critical threshold for the compactness of the binary, the effective potential for the scalar field changes, gets this Mexican shape potential, and the minimum for the scalar field is non-zero, so it signals a deviation from GR. So we could actually analytically understand this. So this would have been impossible if we had treated the theory as an effective field theory. Okay. Is there? Sorry, I didn't stop. There were a few questions, but of course, if you have questions, maybe this.
Maybe just for just a curiosity, can I ask? So are there have people worked on mergers in sort of theories of gravity, modified theories of gravity, which have a vector field?
Yeah, this is what I was mentioning before as Lorentz violating gravity. So
yeah, but for instance, mergers,
No, for mergers. We have an initial value formulation, and if you're interested, I can send you the reference, but it involves tetrads, so nobody actually implemented it on a computer.
Okay, sorry.
The reason for that, no, it's all right, my fault. I didn't mention that, this Lorentz violating theories of gravity Lorentz symmetry can be violated by introducing a Lorentz violating scalar field or a Lorentz violating vector. But there are other, so there are simulations in Proca theories, so vector fields with mass when it comes to superradians, but for mergers, I'm not aware of any, but it could be just my ignorance. There is, however, if nobody has other questions, maybe I'll go to the next class of theories that I want to talk about. There is another class of theories that is somewhat interesting, or it's actually very interesting for something called the DOS class, or So here I write the action for what is called the Hordensky class, which is actually a subset of DOST. DOST stands for, should have written it on the slide, degenerate higher order scalar tensor theory. So this is the most generic scalar tensor theories that you can write that has no ghosts. So in particular, Hordensky is the most general scalar tensor theories that has second order field equations. So the story is interesting. So it was, this Lagrangian was derived in the 70s by Hordensky, and then it was rediscovered in the beginning of the last decade. So it's a hopefully complicated Lagrangian if you look at it. Interestingly, well, it's, yeah, I guess it's not clear from here. It includes also Einstein, Dilaton, Gauss, Bonnet, the theories I mentioned before. So it's a huge class of theories. And the reason why it's interesting is that this provides an effective model for dark energy. So it provides both self-accelerating solutions, so solutions in which the universe accelerates without dark energy, and the screening mechanism I mentioned in the very beginning. So a mechanism whereby GR is recovered on small scales, and deviations from GR are allowed on cosmological scales. So this is something that is being taken very seriously by cosmologists. For instance, Euclid, one of the goals, the main goals of the Euclid experiment is actually to test these theories. So unfortunately for Euclid, gravitational waves already cut a big dent on this Lagrangian. Essentially from the LIGO-Virgo constraint on the GRB, GW170817 constraint on the speed of gravitational waves, and other constraints that come from the requirement that the gravitational waves propagate unabated in the universe, it turns out that you only have essentially one term left in this huge Lagrangian. This already shows you the power of gravitational waves. And this term is what people call K-essence. This was a theory that was introduced again in the 90s, before this whole Lagrangian was known. And it simply involves coupling, well, it's a nonlinear theory in the kinetic energy of the scalar field. So in particular, one could, the simplest K-essence theory you can imagine is one in which you have this X as the kinetic energy of the scalar field, and then you just have quadratic and perhaps cubic or quartic terms in the kinetic energy of the scalar field, and then you couple this minimally or actually conformally to gravity. Conformal coupling is needed if you want to have a non-trivial phenomenology. So this is would seem an inoffensive gravitational theories. It has, however, a very rich phenomenology. For instance, it gives, as I was saying, screening at the level of stars. So yeah, so I have too much material, I guess, on this slide, but let me just focus on this one plot. So what we did in this paper in preparation, which will be out probably next month, we looked at the gradient of the Newtonian potential for a neutron star in GR and in non-GR in this theory. So the ratio between the Newtonian force in GR and beyond GR. For K-essence and for Brans-Dicke theory. So for Brans-Dicke theory, this ratio between the Newtonian force in GR and beyond GR is never one, and in particular, it can grow large at large distances from the star. Whereas for K-essence, which is shown here in red, the ratio between the Newtonian force in GR and beyond GR is always one, up to very large distances from the star, so up to cosmological scale. So this tells you that GR predictions are recovered on local scales, and then unlike Brans-Dicke, and the deviations from GR are allowed on large scales. So this transition radius is sometimes called, well, for a different class of theories, what people refer to as the Weinstein radius. So it's the screening radius of the theory. Okay, so this might be of marginal interest for most of you. You might wonder what happens to the Cauchy problem and to mergers in these theories. Well, as I was saying, they seem inoffensive, but actually when you try to look at, we tried looking at the Cauchy problem in 1+1 dimensions, which is the prerequisite for then being able to perform binary simulations. And we find that, in fact, while for most initial data, evolutions are stable, are well posed, there are breakdown of the Cauchy problem in tiny regions close to critical collapse. So this epsilon here is the energy of the initial data. The sigma here is the size of the initial data. So, and the outcome of the simulation is shown by the color. Gray means black holes, Minkowski in blue. Dark gray is also a black hole. It's sort of problematic, but okay, I don't want to enter too much into the details, but there are regions near critical collapse, so near the threshold for black hole formations where well-posedness seems to break down. So I can talk more in detail about this if anybody's interested. But even in these very simple theories, performing a Cauchy evolution is not trivial. I believe we'll have results soon, even 3+1, but the well-posedness might depend on the initial data. So it's not what mathematicians refer to as global well-posedness. Okay, so I've used up most of my time, but I would skip a few slides, which I added this morning, thinking I would have too much time for my presentation. So I hope you were not too disappointed by the merger results. So I think the bottom line is that we don't, except in a few theories, Brand-Sticker theory, the Morris-Rutherford, perhaps K-essence theories, we don't have sound predictions for the merger, but the results that we have in Brand-Sticker theory show us that nonlinear effects might be actually important during the merger. So it's worth pursuing the goal of making merger simulations, even though it requires lots of work on the well-posedness of the Cauchy problem. So the last things I want to say, perhaps in the last 10 minutes, and then I'll break because you're all tired and so am I, is I want to talk about ring-down tests. So Ajit already and perhaps others before already talked about ring-down tests. So let me just say that, yeah, so there are tests, of course, of the no-hair theorem, and the hairs, which LIGO and Virgo consider as free parameters, are actually the same hairs that we discussed in the beginning of this talk when it comes to the inspirer. So they are the same sensitivities and scalar charges that you can predict in a top-down approach. It's actually difficult to predict, to perform these tests with current detectors, and we might have to wait until LISA or third generation detectors. This is what I show in this slide, but okay, I don't want to spend much time on this. So it's actually difficult to do with current detectors. One thing that could be interesting, however, is to combine the observations we get from LIGO with a different sort of experiment, another gravitational experiment in a sense, but based on photons, which is the Event Horizon Telescope. So you're all familiar, I guess, with the shadow of M87 star, the black hole in the center of M87. And as you know, that is sensitive to the light, what we call the light ring, or the circular photon orbit of that black hole. And interestingly, that is the same physics that we test with quasi-normal modes. Quasi-normal modes are in fact produced near the light ring of the final black hole produced by the merger. So in fact, you can show this explicitly in the geometric optics limit. The frequency of quasi-normal modes in the geometric optics limit, in the high L limit, are proportional, or at least the real part is proportional to the frequency of the light ring. So this, I think, opens interesting prospects for combining the results of the EHT with the results of LIGO. I don't think this hasn't been done by LIGO yet, so we try to do it at least in a toy model, in which we assume that quasi-normal modes are measured with 1% error. So we assume we see 4 quasi-normal modes. The L = 2 mode with the first the fundamental mode and the first overtone, and the 3-3 mode with the fundamental mode and the first tone with 1% error. And then we try to compare how our results fare with respect to the EHT. So what they do in the EHT is to try to put constraints on parametrized black hole metrics. So again, I'm sorry I have too much material here, but essentially what they do at the EHT is to deform by hand, really, Schwarzschild or Kerr black holes by adding free parameters, a little bit like we do in LIGO and Virgo, or like they do in LIGO and Virgo by perturbing the post-Newtonian parameters. So they do the same for the Schwarzschild and black hole, the Schwarzschild and Kerr space-time at the EHT, and then they try to put constraints on these parameters. For instance, in this, what is called sometimes the Rätsalva-Zydенko metric, they put constraints on this parameter A1 and epsilon, and the allowed region would be this blue region here, not overlapping with the red. And these are the same parameters that we could constrain with gravitational wave detectors. So based on this preliminary study we did, we could constrain, for instance, this parameter epsilon to much better accuracy if we could measure 4 quasi-normal modes with 1% error. So I don't, we haven't done this analysis with the real LIGO Virgo data, but this is something that could be interesting when it comes to comparing to different, to combining different experiments. Okay, the last really 5 minutes, and then I promise I'll break. I want to talk a little bit about, first of all, I don't know if there are, so this concludes my, if you want, review of the effects that we can see in the spiral merger ring down. We talked about dipole emission and scalar charges or sensitivities in the spiral. I gave you a review of the essentially the 2 or 3 theories for which we can make some predictions or have some ideas about the merger. And as for the ring down, so this also concludes my review of the ring down. So to me, the most promising avenue there is either to use parameterized ring down tests to put constraints on specific theories. So to go from parameterized tests to top-down tests of the ring down, and the other possibility that I find very interesting is to combine with AHT. So in the next part of the talk, if there are in the last 5 minutes, as a matter of fact, if there are no further questions, I want to say a few things about black hole superradiance and discuss how stochastic backgrounds can put constraints on the mass of bosons. I believe this is something that Victor didn't talk about yesterday, although he talked about superradiance. So if there are no questions, I will just show you a couple more slides, and then I would break for if there are final questions. So Victor talked already yesterday about black hole boson condensates. So he talked in particular about superradiance. So let me just remind you very quickly the basics of this process. So superradiance is essentially the wave equivalent of the Penrose process. So we know that, so you know from textbooks that if you throw a rock at a Kerr black hole and the rock splits in two inside the ergo region, because in the ergo region you have negative energies, fragment 1, which falls into the black hole with negative energies, can transfer essentially an energy to fragment 2, which emerges from the black hole with larger energy. So Penrose process is a way to extract energy from a black hole. So, and you can actually perform the same energy extraction procedure by throwing a scattering wave off a black hole. So, and this is called superradiant scattering. It happens for frequencies of the wave which are less than a multiple of the frequency of the horizon. Omega here is the frequency of the wave, and omega is the frequency of the horizon. M is the azimuthal quantum number of the wave. So this is the superradiant. This is the superradiant scattering condition. For this, of course, you need high spins because you need a sizable ergo region. So superradiant scattering or the Barausse process are not instabilities. They're a once in a lifetime, if you want, energy extraction procedure. So you throw your wave, the wave gets scattered off and never comes back. So you extract some energy from a black hole, but this doesn't cause an instability. However, what you can do is to actually put a mirror outside the black hole and reflect the wave back. And this actually can give rise to an instability, which is called black hole bomb instability. And because you essentially focus the wave back time and time again, the wave then is scattered back by the effective potential, which is due to the centrifugal barrier, as Peter was explaining yesterday. So you can come up with a process that goes on and extracts more and more energy from the black hole. And interestingly, this works also for a mirror at or very near the horizon of the black hole. So this is what Peter talked about yesterday when he referred when he talked about echoes. In fact, these mirrors could be a toy model for instance, for firewalls, if we believe firewalls, and if we believe firewalls can be modeled by partially reflected mirror, and they could give rise to a secondary pulse in the ring down. In fact, here, yeah, which I show here. So this was a 2014 paper, so before the LIGO detection, where we showed that if we put, for instance, matter at far away from the black hole, matter would act as a mirror outside the black hole and reflect the signal back and give rise to an echo. And in that paper, we also showed that if we put a mirror at the horizon, we produce a secondary echo. So now echoes have become very fashionable, of course. There were even claims that they were seen in the LIGO data, so I don't take a stance on how reliable those claims are, but this is interesting when it comes to testing near horizon exotic physics. What I want to show, however, very briefly, is that Peter mentioned, I think, yesterday, the same instability that you can produce with mirrors is actually produced also for boson fields with mass. So this was recognized again back in the 70s by, it's always the same people, Damour, Derouet, Ruffini in 1976. They showed that if you have a spinning black hole and a massive boson field, this doesn't work for a fermion, by the way, only for a boson due to Pauli exclusion principle. So if you have a spinning black hole plus a very light massive field, black holes with spin become unstable, and the instability region depends on the mass of the boson. So this is what I show in this figure. There are instability islands or instability regions, which are color-coded with the mass of the boson. So these are regions where black hole spins cannot, where black holes cannot exist. So if we measure very large spins with LIGO or LISA or any other experiment, we could actually put constraints on the mass of the boson. But more importantly, this instability can also be followed through to its endpoint. So in fact, this is one of the few cases in physics in which we can also calculate the endpoint of this instability via simulations or also analytically. Sorry for, yeah, I'm almost done. Yeah, so this can be understood quite easily. If I go back to this slide where I have the superradiance condition, I mentioned that the frequency of the wave must be less than a multiple of the horizon frequency through the azimuthal quantum number m. So this tells you already that something that axisymmetric waves cannot give rise to superradiant instability, because axis symmetry corresponds to m equals 0. So the first mode that can become superradiantly unstable is the dipole mode. And in fact, what we see is that the endpoint of the instability is exactly the formation of a rotating dipole around a spinning black hole. So this is again an isolated spinning black hole with high spin, surrounded or by the vacuum with a scalar field with mass in its vacuum state. So what happens is that the scalar field evolves and develops a rotating dipolar configuration at the expense of the rotational energy of the black hole. So the scalar field extracts energy from the black hole and starts rotating. And of course, and this happens on a very rapidly on a time scale of years for LIGO black holes. And then you end up with this scalar wig that co-rotates with the black hole. And this produces, in general, gravitational waves, because whenever you have something rotating, if you have a rotating dipole in GR, simply because of the quadruple formula, this will produce gravitational wave emission. And this, again, happens for isolated black holes, too, not just for black holes in binary. So it could happen for the black holes produced by the merger in a LIGO-Virgo binary, but it could happen also for isolated black holes in the universe. In fact, it will generally happen for any isolated black hole with large enough spin. So what we did, I believe that Vitor didn't talk about this yesterday, according to what he told me. So this is work I did with Vitor and other collaborators a couple of years ago. So what we did was to take astrophysical models for all the isolated black hole binaries that we can see in the universe, that we expect are there in the universe, which are much more numerous than those that we expect to reside in binaries. And we computed what the stochastic background of gravitational waves would be from these rotating scalar wigs that I just described. And the stochastic background that we get is typically huge if the scalar field is in the right mass range. So for instance, LIGO, already the LIGO 01, or certainly 02 bound, could exclude scalar fields, or if you want, these are also called axionic light particles. They are a model for dark matter, as Vitor eloquently explained yesterday. The LIGO already excludes masses for the boson between 10 to the minus 13 and 10 to the minus 12, already from the stochastic background. I know that LIGO people have tried also to look for resolved monochromatic sources. I personally think it makes no sense because this is already excluded, although of course it's something that one can do. So stochastic backgrounds already exclude this range of masses. And with LISA, we'll be able to go to much lower masses, which incidentally are much more interested for cosmology. I think I'll stop here. I will skip this slide. Maybe let me just say that by the same argument, you can also exclude, by the same argument with the stochastic background, you can also exclude that all black holes in the universe have mirrors or firewalls near their horizon. Because again, if they had a firewall or a mirror near the horizon, they would produce, they would go unstable, they would produce again gravitational wave emission. And because there are so many isolated black holes in the universe, we expect that this would give rise to a very large stochastic background already detectable by LIGO. I should stress again that these predictions are based on the whole population of isolated black holes in the universe, because since some of the audience here is in LIGO, I know that, that there are papers by LIGO people who actually did a similar computation, but only included the merger remnants. So only the black holes produced by mergers of binaries that produce background. So here we're including all the population of astrophysical black holes that we expect in the universe, be it those isolated or in binaries. So I think this already excludes the possibility of having echoes, even though of course one could and should continue to search for echoes in the resolved signals. Okay, I think I'll stop here because I've been talking for way too long. I had a last slide on Lorentz violations and universal horizons, but if anybody's interested, please ask me. So what I want to show in that slide is that Lorentz violations also produce this near horizon exotic physics. But let me just wrap up my talk by essentially reading my conclusions. Well, in the first part of the talk, I showed that GR extensions are already constrained by the absence of dipole emission in binary pulsars. So I showed you how that can essentially kill many gravitational theories. So it puts very strong constraints on Brans-Dicke type theories, on Lorentz violating gravity. And there are cases, however, in which non-perturbative physics, and this is what I refer to as scalarization, can still give rise to interesting non-perturbative effects in binary systems. So I don't think it's a wasted time to keep exploring the inspiral of binary systems in a top-down scenario, theory by theory, because there are theories in which surprises can happen. And I explained about black hole scalarizations. I explained about screening of local scales, which is another nonlinear effect. That I also find very interesting. So I think there's room for much more work in this area in the future. The real problem is that whenever deviations from GR are small, the perturbative predictions that we get, also for the spiral, are easy to map into the parameterized formalisms that people in the data analysis community use. So this parameterized post-Einsteinian formalism that, for instance, Jit essentially and Arun also talked about in their talks. The constraints can be significant, but really what I think is interesting and what's the holy grail of this area of research is really to try to compute non-perturbative effects during the merger. And I think I gave a dire, well, maybe too pessimistic review of that part of the a research program. So that requires certainly technical skills. It requires showing that the Cauchy problem is well posed, but the reward, I think, will be huge because we would be able to discover possible non-perturbative effects during the merger that we might or may not observe in LIGO binaries. So I gave the example of neutron star dynamical scalarization. For instance, that is not ruled out yet based on the LIGO results. So I'm quite excited I'm quite excited by the prospects of seeing that effect, perhaps with third generation detectors. And when you have this parameterization, these non-perturbative effects, it's very difficult to cast them into parameterized formalism. So we might have to rely on a theory by theory approach in which we produce waveforms that are then used to analyze the data, because lots of information would be lost if we just rely on perturbative approaches. Okay, I apologize for the very long presentation. I guess everybody is exhausted and so am I, but if there are any questions, I'm happy to answer them now or later in the discussion session.
Yeah, let's thank Enrico for such a nice talk. And yeah, if there are immediate questions, we can take it right away. Any question from the audience?
So I have a question.
Yes.
Hi, Enrico. So in the end, when you were talking about the stochastic background coming from firewalls or any such modifications, usually, I mean, the time scale is very small. So why do you expect a stochastic background if there are firewalls or any like mirror, or there's a reflective membrane in place of the horizon?
Hello?
Hi.
Sorry, either you broke out or I didn't understand the question. So
sorry.
you expect a very small time scale? Sorry.
Yeah, so I was asking that.
Can you repeat the question?
Yeah, sure. So I was saying that when you were saying that the stochastic background is kind of ruled out, but I'm saying that for a firewall or any kind of modification to the horizon, the echo time scale is very small. So it's logarithmic of the mass. I think you wrote there somewhere. Yeah.
Yeah, exactly. But that is still so. If you so in fact we do two things in this plot. So first here we put a mirror, a perfectly reflecting mirror, and that's an important point, at a Planck length from the horizon. And then the time scale of the instability is the dynamical time scale to within a factor of order a few. So even if you put a mirror at the Planck scale, the dependence of the time scale of the instability on the epsilon distance at which you place the mirror. So if you place a mirror at distance epsilon, the time scale on which the instability occurs is still of order the mass times log epsilon. So
Yeah.
even if you put it at a Planck distance, because the dependence is logarithmic, you still have a very fast instability. So that does not, in fact, this does not prevent this effect from happening, because the time scale is much smaller than cosmological time scale. So you have to think that these black holes, they're formed very early on, so they live for giga years. I don't know if this answers your question.
Yeah, so I'm saying, so there is still a window like where they can be detected, right? I mean, it's like.
Yeah, well, if you want a totally honest answer, even though I don't like echoes, yes, there is. If you allow for viscosity, I think Bitter, I don't know if it was you who asked the question or somebody else asked the question to Bitter, I think yesterday in the question time. So if you have a partially reflective mirror at the horizon, so if you allow most radiation to fall into the black hole or into the horizon, and only a few percent, I forgot the exact number now, but I think
6%.
So if you allow some radiation if you allow for a partially reflective mirror, then yes, this instability can be quenched. And actually you don't need much. You don't need much. I think if you have just 10% transmissivity, then it could work. Of course, there's a question. So this corresponds to, in a physical model, to assuming that the object, this black hole mimicker, is made of matter with very high viscosity. Because if you have a neutron star, you can model a neutron star with a mirror, with a Schwarzschild spacetime with a mirror, if you want, and the viscosity of the neutron star would correspond to essentially a totally reflective mirror. So you would need exotic matter with extremely large viscosity to have such a physical scenario. Whether that is possible or not, I'm not a theorist, so or not that kind of theorist. So when there are ideas, there are people who claim this could happen, for instance, in non-commutative geometries and other. There are many ideas, but I don't think anybody ever showed convincingly that such high viscosity is allowed.
Okay, thank you.
This is what.
Are there any other questions from the audience?
Hello, can you hear me?
Yes, I can.
Hey, thanks. Thanks for the nice talk. Actually, I would be interested to hear what you were going to say about that slide. Is that slide you had to skip, the one including the universal horizons? If that's okay.
Yeah, of course.
Thanks.
Yeah. Okay. This again, I could give an entire talk on Lorentz violations, but yeah. So in this slide, I wanted to talk about what it means to have Lorentz symmetry. What I mean is that the very concept of black hole, think about the concept of apparent horizon in terms of congruencies of light rays, is based on the fact that photons can travel at finite speeds. So if you have a violations of Lorentz symmetry, as I think perhaps Ajit talked about in the previous slide, you have in the previous talk, you can have dispersion relations of this kind in which you have nonlinear terms. So in fact, LIGO attempts to constrain this quartic term in the wave number. What is problematic, or well, I will show it's not problematic. What makes you think when you look at this nonlinear dispersion relation such as that? Well, first of all, it clearly breaks Lorentz symmetry because omega and k are on different standings. Looking at Lorentz related. The other thing is that if you take the derivative of omega with respect to k, the group velocity, you find that the group velocity diverges in the UV. Hello? Yeah, okay, my computer says my internet connection is unstable. I hope I was audible. So when you compute the group velocity diverges in the UV, and this raises this corresponds to instantaneous propagation of perturbation. So this raises the question of what does it mean to have a black hole in a theory in which you have instantaneous propagation. So theories of this kind are what we call Hojava gravity, in which we parameterize Lorentz violation by a scalar field, or Einstein's theory, in which we parameterize them by a vector. But that's, if you want, that's a detail. So the interesting is that, in fact, there is a concept of horizon that survives, even though you have instantaneous propagation of modes, of gravitational modes. And in fact, this is some old work I did in 2011 with Jacobson and Thomas Soteriou. So we looked at spherical symmetric static black holes in these theories, and we solved really the field equations for the geometry. And then what you see is that the Penrose diagram. This is on the left, you see the Penrose diagram of Schwarzschild. The Penrose diagram of these black holes is, in a sense, similar to Schwarzschild, but it has a very important difference. There is a preferred foliation. There is a preferred time. There is a scalar field that sets the time, the absolute physical time that you can define in this series. This is why they break Lorentz symmetry. So surfaces of constant time, of constant absolute time, are shown here by solid lines. And as you can see, near spatial infinity or near null infinity, they look like the Schwarzschild, the t equals constant surfaces, but then they deviate very much in the strong field. Suppose the would be the event horizon. And suppose you have so this would be a horizon, this line here would be the horizon, provided that your light cones are 45 degrees, like you have in Schwarzschild. And now suppose you have infinite propagation speeds. You could actually easily escape from that point, from the horizon, and you could actually propagate everywhere in the future of the t equals constant surfaces. Now, and this of course would seem to imply that there is no event horizon in this theory. It doesn't make sense, so we should be really worried. What we found, very surprisingly, if you want, is that there is one surface, which is the red curve here, in which surfaces of constant absolute time actually enclose the central singularity. So if you're sitting at one of those surfaces, which are also surfaces of constant radius, simply because the absolute time has to increase if you go to the future, you can't escape. So even if you have infinite speed, you can't escape. And so this provides a way to define a horizon, even in theories with infinite propagation speeds. And this is what we call universal horizon. So why was I making this comment here? Because actually, it turns out that this horizon seems to exist only in spherical symmetry, and it seems that when you go away from spherical symmetry, it might become unstable and form a finite area singularity. So one of the things that I'm conjecturing is that, even though I haven't tested it rigorously, is that the bounds that we place on the stochastic backgrounds on the black hole mimickers could actually perhaps be used to exclude, to actually kill Lorentz violating gravity completely. Because what we expect is that, again, when you go away from spherical symmetry, you would produce a finite area singularity, which would behave just like a black hole mimicker or a firewall or a hard surface. Yeah, so this is what I wanted to, so yeah, so echoes or stochastic backgrounds could also be a way to test Lorentz violations, and in particular the concept of horizons in Lorentz violating gravity, which is not at all trivial. I don't know if this is what you expected, but that's what I wanted to say. Thanks for asking.
Thank you.
Thank you. Yeah. Are there any other questions from the audience? Okay, so if not, I have two small questions to Enrico. One is when you talked about this black hole mimickers, I guess you always have in mind the exotic compact object with some matter with, like
That's what I
boson
meant,
stars
yes.
or Gravitational star. But there can be other geometrical configuration like wormhole or fuzzball, and I think they will evade the constraints that you have presented here.
No, I don't think so. In fact, yeah, so it's my fault because I didn't explain exactly what we compute. So these predictions just relate to two things: the astrophysical models, which we might get completely wrong if you want. That's a possibility, but I don't think since the signal to noise ratio of the stochastic background is thousands, I don't think we can be wrong by that factor. And the other thing we do is to model whatever black hole mimicker as a Schwarzschild geometry, is a Schwarzschild exterior geometry with some boundary conditions at finite radius. Now, I think for a wormhole, this is totally fine. And also for a gravastar, I think as long as the matter of the gravastar doesn't have very large viscosity. So I discussed with Emil Mottol about what would be a better model for what would be a model for the viscosity of a gravastar, but I don't think we know. So yes, there are these things depend on just two things: the viscosity of the matter, and yeah, and the astrophysical model. For a wormhole, I think the same will happen, because if you can think of your radiation as going through the wormhole, but then it will be reflected back by the effective potential on the other side of the wormhole. So in fact, I think the same results will apply to wormhole. In fact, this was the Vitor. I think I have a slide on this. So these are the echoes in the case of a wormhole. This is a paper by the famous paper by Vitor. So they show that these echoes, which are responsible also for these stochastic backgrounds, are there also in the case of wormholes.
Yeah,
I don't know if
I
this...
think in this paper, the wormhole was assumed to be just Schwarzschild at the exterior. But if you choose a more proper wormhole solution like the Damor-Solodukhin, or maybe some wormhole in the Brainwald case where exterior is not Schwarzschild, there may be some modifications which can still make it more viable. But that
yeah,
was just
well, yeah, it could be, although I don't think it's very likely, because on the ergo region instability. So either these modifications are very different from Kerr, and in particular the ergo region is much smaller, or I don't see how having a slightly different exterior than Kerr can save the day. First of all, yeah, we can't just use spherically symmetric wormhole solutions for this exercise, because, sorry, it wasn't clear. For this instability, it's crucial that we have spins. So what also in the astrophysical models is not black hole candidate spins are zero. So if all black holes in the universe had zero spin, this effect wouldn't be there, because it's related again to the black hole bomb instability. If you tell me that that your exterior is very different from Kerr and it has no ergo region, then I might buy this. But then I don't know of any rotating wormholes with exterior with no ergo region, that has no ergo region. So it's a possibility, but I don't know enough about these solutions.
Thank you, Enrico. And yeah, I guess that's all for your talk. If there are no other questions from the audience. Yeah, so we can now start the discussion session. So from all the audience, and there are other speakers also from previous day and also today, Enrico, Ajit, Arun, and I'm not sure whether Shukant or Vitor is here. But if there are other questions that the audience has had either yesterday or today to the other speakers as well, I mean, they're free to ask.
So if I may start asking one question. So we have tested general relativity in a very limited set of parameters. maybe within the solar system's test, we are confident about general relativity. And also we have not tested general relativity much when there is a matter involved. I mean, when the solutions is a solution, not the vacuum solution. So it seems there is a large parameter space still available where the theory can break down even before the quantum gravity. Classically, there is a modification of the theory. So what do you think about the motivation? Do you think that this is enough motivation to go for it or look for it? Or is there another, somehow more motivation is possible?
Yeah, I think this is to all the speakers about their opinion on going to theories beyond GR.
I'm not sure if I understood the question, and I don't want to monopolize the discussion since I'm very tired. But to me, I'm not in love with any particular theory beyond GR. So, and I agree with all questions and points that were raised that we have no deviation from GR, no evidence for a deviation from GR. But I think it's still important to consider these deviations because gravitational wave experiments are not. I mean, you don't find a deviation from GR if you don't look for it. So you need to have a very good idea of what you're looking for. And so it's not, I don't think it's wasted time. Actually, to the contrary, I think it's very important to have an idea of what, especially non-perturbative effects might look like in order to look for them in the data, because as Ajit or Arun can tell you, when you use these parameterized models, if you want the power of these parameterized deviations from parameterized models in detecting a deviation from GR is smaller than what you would get with a tailor-made waveform. Maybe this doesn't answer your question, but maybe it's something that we can discuss.
No, I think I agree with you. Since there is also, even observationally, there is a large parameter space is available where we have not tested the theory. And we cannot test a theory if there is no alternative available. So I think in that case, it is a very well motivated search.
Yeah, and also it is like you said, if you want to carry out tests of GR, like parameterized test, even in the case of, I guess what you meant is our bounds from the binary neutron star or neutron star black hole, that kind of objects where there is matter, at least in one of the objects. So it is going to be the case for quite some time that the bounds are going to be weaker in some sense, because we also have to estimate the equation of state related parameters in the full parameter space, and they do affect the overall precision with which we can find the alternative the deformation parameters. For example, if you look into the binary neutron star, the GW170817 one which we did, the bounds were not as spectacular as one would have thought, given the long duration of the signal and so on. So it is so it is also going to be, if you want to invoke matter, that would involve you're also involved in parallel parameters, which will have to be estimated from the data, and that's also going to be challenging in the near future, at least, I think.
Yeah, I also matter is sorry, go ahead.
No, go ahead, Enrico.
No, I just want to say that in the case with matter, we also have to worry about degeneracy with the equation of state, right? I mean, if we consider deviations from GR and equations of state at the same time, it might get difficult to disentangle the two effects, since we were talking about matter, I think. That's all I wanted to add.
Yeah, so in my view, clearly as physicists and astronomers who would do experimental and observational tests of the nature, there is always room for testing our fundamental theories. That is no question about that. What would be nicer is that it would be nicer to have some real serious alternatives that will seriously contest GR, that would not suffer from various issues of formulation and so on. So in that sense, I guess it's partly, I assume that it's partly due to not enough smart people spending enough time on solving and trying to solve those equations of alternative theories or coming up with alternative theories. But I'm hoping that in the coming years, some actually solvable equations of alternative theories can be solved, and alternative predictions can be made also.
Ajit, if I may make a comment on that. So I think it's not a question so much of solving difficult equations, it's just that the energy scales just conspire against us. So these are all really very classical objects. So any deviation you have from them, from any, quantum gravity effects or whatever, just take an effective field theory approach. The energy scales are really against us and the effects will be very small. So I think no matter what you do, you will get a small effect unless there's some really big surprise in this situation.
But
So,
don't you think,
are you referring to the quantum gravity inspired models, or even generic things like F of R theories, etc.?
Anything, right? So, I mean, especially the quantum gravity ones is the one I have most in mind, but even for the others, I think the argument should apply broadly.
So, Ajit, I had one question in this regard. So, in one slide, you mentioned about this prior to the GR and non-GR theories. And you sort of mentioned that that prior is much less than 1 because there is more chance to get a GR theory. Now, I'm just wondering whether there should be some energy scales also associated with it, as Bodri mentioned. So GR is sort of, we know, is the correct theory or at limit of a correct theory in the IR case. So maybe those priors should also involve some energy scale, I mean, up to which we have tested, or do you have any comment on that?
Yeah, I guess strictly speaking, yes. I was taking it loosely only, and the fact that we have had several observational evidence that GR is preferred. Then if you want to believe in a new result that somehow disfavor GR, that we need to have a huge amount of confidence in that new result. That is what I meant by that the prior odds significantly favor GR. But you are right in the sense that GR has been tested only in some specific region of the parameter space, and yeah, in principle one has to invoke a parameter space dependent prior.
Well, I mean, the energy scale we test is the size of the black hole, right? So that's sort of the length scale, it's like tens of kilometers, let's say.
Yeah, but can I say something about this, Badri? So
yeah,
you're totally right that the energy scale is that of the size of the black hole. So if you convert it in electron volt, it's around 10 to the minus 12 electron volt. So it's a tiny energy scale, but compared to the Planck length or to the Planck scale. But if you consider deviations from GR that are built not as models of quantum gravity, but as models for reproducing dark energy phenomenology or dark matter, then I think we're in a better position to put meaningful constraints. This is what I was trying to say by, for instance, regarding the backgrounds, the axion-like particles. Well, not so much with LIGO, but certainly with LISA, we'll be able to reach even smaller masses, which correspond to cosmological scales. Because the smaller the energy scale, the larger the length scale. So if we go to larger scales with LISA pulsar timing arrays, we would be able to probe cosmological scales. And also regarding the comment, I think it was Ajit, who was asking essentially for more theories for which we can make predictions. I think we can, there's been lots of work on theories with cosmological applications lately. The thing is that we don't even get to the point at which we need to produce waveforms to compare to the data, because they're already ruled out, for instance, already by the propagation effects, for instance, or by the fact that the Cauchy problem breaks down. So I think gravitational waves have been playing a big role in that, even though we didn't get to even to the point of comparing to the data. So the very fact that the waveforms that we observe are close to GR or that the propagation is close to what we have in GR is hugely informative for our for us model builders. And also regarding gravity, what I showed about Lorentz violating gravity. So maybe we can discuss whether Lorentz violating gravity is a viable model for quantum gravity, but it has. And quite surprisingly, there are effects that extend to small scales, and the theory is almost ruled out by gravitational wave physics. Even though, again, it's not the LIGO data, it was the binary pulsar data, but it's almost ruled out. And that's one, albeit controversial model of quantum gravity. So I'm not very pessimistic. It's just that not all theories, they get to the stage at which they can be compared with the nice chirping signal that we see in LIGO. They're killed by the gravitational wave observables even earlier, by the requirement that the wafers are not hugely different from GR, by the requirement that you can have that you should have a well-posed Cauchy problem, by propagation, by the requirement that that black holes should not be extremely different from GR. So I think even though we don't see it, and I think we're contributing a lot in understanding these theories. I think that the LIGO bound from GW 1708-17 essentially killed the whole scientific motivation for Euclid in one day. So I'm not. Maybe it's because I work on this, but I see the contribution of gravitational waves as being very major in this respect.
Yeah, so I do agree with you. I don't mean to say that this is not worth doing or anything of that sort. It's just that for the present LIGO with binary black holes, especially for the present stellar mass black hole, it's a different situation. Once we reach LISA, so higher masses and more precision measurements, then it's a different thing altogether. Yeah.
Yeah, but Enrico, I also know that these theories which are ruled out by the GW 1708-17, later on people are trying to put again them back on track by using the Weinstein mechanism. They are sort of arguing that at the local length scale, it's mostly GR, so that effect would not matter. But at large cosmological length scale, those terms can still contribute.
Yeah, so, but I know those attempts, but I've seen only toy models. I think you're referring to the fact that the bounds that LIGO puts are very close to the cutoff of those theories. So you can't treat them as effective theories. And then they say, well, there could be some unknown UV physics that saves the day. But I haven't seen a model where they do this beyond toy models. So I think the burden is on them to show that they are viable. But yeah, it could be.
But if we, believe them, their results, or if they are able to show some concrete computation, then would not that mean that any alternative theory that you have, you can sort of hook some sort of Weinstein mechanism to make them work at the local scale of GW, and still they will survive? And
no, but again, you have to show it. As long as you say it, it's I think the burden. I mean, to put it bluntly, something is science if it is falsifiable, right? So if you just say there could be some unknown UV physics that saves the day, and you can't make predictions for what the waveforms are or what the speed of gravitational waves is, that is not science. You need to provide to say what the UV completion is. What they're saying is that the physics of LIGO depends on the UV completion of the theory, but they don't know the UV completion.
Yes.
So yeah, it could be, but you have to write the UV completions. The UV completion for those theories has been, there is a paper by Claudia Deram, I think, a couple of weeks ago, where they write the UV completion for some of these theories, but nobody has ever shown that UV completion saves screening or saves the propagation, the speed of gravity being equal to the speed of light. I don't know. Maybe I'm biased, but that's my understanding of it. It's a shame we don't have anybody working on those UV completions here, I think.
So any further question from the audience to the speakers? Okay, so I think if there are no further questions, maybe we can come back for Professor Bodrikrishnan's talk at 4:30, and we'll take a small 20 minutes break. Oh, I think there is a question. Shomodip. Yeah, so Shomodip, please go ahead.
So actually, this is a question for all of the speakers. So I was actually waiting for if Dr. Cardoso or Dr. Bose, if they come. So it's a question which I was thinking from tomorrow. So as yesterday, sorry, I'm sorry. So as many of the speakers pointed out that we are using GW to differentiate between different between dark matter, dark energy, different GR models, modified GR models, as well as compact objects which are not black holes. So my question is, if it is possible that if we consider that there is also a body which is not a black hole, some kind of other exotic object, as well as there is some modification of gravity. So is it possible there will be some sort of overlap or some sort of mimicry between one or the other, which will uh, suppress the detection of one or the other? So
Are you asking, I'm not sure I understood the question. Are you asking whether the presence of another body, a third body, can mimic a deviation from GR, or did I?
He's asking to violate GR and have a non-black holes.
Yeah.
Because
So you want?
So I think he's asking about a degeneracy between non-black hole and non-GR theories. So can you break the degeneracy?
But in general, to have non-black holes, well, if you exclude neutron stars, you need non-GR, right?
Yes.
No, but wormhole solutions, for example, can be in GR, but they are non-black hole. So I guess the question is generically that can we make a difference between non-GR and non-black hole candidates? So is there a degeneracy between the two, and if there is, how can we break them? Break the degeneration?
Well, I think they're very degenerate in general, because you can parameterize during the spiral a non-black hole with a charge, an extra charge with respect to GR. You can parameterize it during the ring down with a hair. And those are both concepts or quantities that you introduce generically when you deviate from GR. So at least during the spiral and the ring down, I think there's a huge degeneracy. Not sure about the merger, but the merger, we don't have predictions for neither non-GR or non-black holes. So I think it's hard to say. But I think personally, it seems to me that it's highly degenerate, as you would expect, since in most non-GR black holes, or non-black holes, as you call them, you introduce exotic fields, which can be, you can move to the left-hand side of the Einstein equations and interpret them as modifications of GR. But I don't know, maybe somebody has a more knowledgeable answer to that.
So can I just ask one question, since Somadeep, I don't have an answer to the question which Enrico posed. So this probably was addressed in Victor's talk, which unfortunately I missed. But which black hole mimickers are ruled out? Are gravastars completely ruled out? Are fuzzballs ruled out? Are wormholes ruled out? What's the one-word answer? Maybe this is to Victor or other experts on this, not directly to Enrico, but maybe you can also chime in.
I can say what I think, but I don't want to, if somebody else wants to answer this. Otherwise, I'll say my opinion very briefly, is that, again, to falsify, science is something that is falsifiable. So if you want to to confirm or rule out black hole mimickers, you need sound predictions, and I don't think you have those for gravastars or wormholes when it comes especially to the pre-merger phase. For the post-merger phase, you have a generic prediction, which is echoes, but then again, we don't know how perturbed gravastars will behave because we don't know the equation of state of the fluid, even less for more exotic black hole mimickers. So it's hard to make sound predictions. The only sound prediction is the presence of echoes, but even that could be is subject to a number of assumptions about the viscosity, etc. So I don't think we're anywhere close to ruling out those possibilities, but not because of, it's not fault of the data. I think it's fault of the inadequacy of the model. This is my personal opinion. But yeah, maybe if Vitor were here, he would have a different answer. But this is my impression.
Thank you.
Are there any other questions?
Well, can I ask one more?
Okay, sure. Yeah.
So since you mentioned modified theories of gravity, what about conformal gravity? I mean, wild tensor, Mannheim-Cazenas gravity, and others. Are there any works along those lines?
Yes, you're asking me. I don't know enough about. Yeah, but yeah, I personally don't know enough about those. I don't know if, for instance, if solar system tests have been analyzed. What is the limit to GR? I personally don't know enough about those to give an insightful answer.
I think Philip Mannheim has done work. I think Tuft also had a paper on this maybe a decade ago. As far as I know, it's consistent.
No, I know the papers, but I don't know enough about the theories. I don't know if anybody analyzed. Yeah, so all these theories require a huge investment of time.
Yeah, I think those are fourth order theories. That's why that's.
Yeah, I talked about K-essence. I spent the last year working on that, and we still are not done. And just in spherical symmetry. So I don't know if anybody looked at those.
Thank you.
Okay.